So we are here to talk about we are building this feature in community for I think a couple of months now, and so we are here talking about two things. One is application history server and the timeline server. So this is the agenda. We'll just talk about who we are, why we need little bit history server, application history server. What is application history server? What is timeline server? What is the differences? And what is the motivation for each of them? And then we'll talk about what is the future. Because not completed yet, so we'll little bit talk about what we'll be doing what are in the future releases. Who we are. I'm Mayank Bansal. I'm a Hadoop architect at eBay, Apache Hadoop committer, Apache Uzi PMC and committer. Currently, I'm leading Hadoop core development for Yarn at MapReduce at eBay. In the past, I've worked on scheduler, resource managers, distributed systems, data pipeline frameworks, and all that. Lot of fun stuff. He's Shiji. He's software engineer at Hortonworks, Apache Hadoop committer, and Apache Samza PPMC and committer. So let's talk about why we need new history server. We already have, most of you knows we already have the job history server. So why we need a new history server? So we have MapReduce job history server, which works well. But there are little motivations we have for which we need to implement the new service where we can actually get the application-specific data. The only problem with the job history server is only customized for MapReduce. It's not generic enough where it can cater any kind of application. So if you are running MapReduce, only MapReduce, this is good. You don't need anything else. The storage is HDFS only. You can store all the storage. Whenever the MapReduce job finishes, store its historical data on the HDFS. You don't need anything else other than HDFS if you're just using MapReduce. And for MapReduce job, it actually scales well. The storage is very much specific to MapReduce. It has all kind of counter information, which is very much specific to MapReduce, mappers and reducers information, which is not relevant to any other application other than MapReduce, right? And if you're using only MapReduce, you're good. You don't need anything else. But if you're not, so this is a paradigm shift from Hadoop 1 to Hadoop 2. Hadoop 1 was a batch processing system, and we only had MapReduce. So that job history server works well. When in the community we developed the Hadoop for the Hadoop 2, we developed MapReduce for the Hadoop 2. We actually very much specifically wrote the job history server very much specific to the MapReduce. But the paradigm shift is so now we have HDFS, Yarn, and the MapReduce. You can run on Yarn, Thais, other applications, Storm, Spark. I think you guys have already attended so many talks where you discuss that how you can run so many other applications other than MapReduce. So this is the paradigm shift. And if you have all these kind of applications, then definitely you need the historical data for those applications to do all kind of analytics. You need this historical information for all kind of debugging, all kind of information about your jobs, how your job behave. And if you are not, we don't have any solution as of now where you can actually get all that information. So this is a little bit about Yarn. I think you guys already seen this diagram maybe a million times. So I'll just skip that. This is just to give the background of the Yarn. So issues with the current job history server, right? There are a lot of, as I said, there are a lot of drawbacks which we have in the job history server. And if you have any other application other than MapReduce, we don't have any solution which can cater the needs of history. So what happens is, yes, you have a running job, and even if you have a completed job, your RM stores all the information, right? And it caters and keeps the historical information. But what happens if RM crashes, right? And you lose all the data. And once you start the RM, you will not have any other information of the job. You cannot go and look back what happened to my job, because the RM doesn't have that information anymore. So RM has, resource manager has a hard limit. It's a configuration. As of now, I think it's 10,000 or something default. So you can specify, you can keep 10,000 application and in the memory of the RM, and you can go back and look at the 10,000 application. But this is a hard limit. As soon as if you're running the loads of eBay, then definitely that limit is very small. So, and then the newer jobs will replace the older jobs in the memory, and you will lose the historical information of the jobs. So this is the hard limit. You can configure it to higher limits, then you will hit the limits of memory into the RM, right? So you don't want to do that. You need another service which actually designed for this kind of service. What happens when you want to upgrade updates, right? You continuously upgrade your cluster, you restart your resource manager to put new features, new patches, whatever. You do upgrades. And in those scenarios as well, you will lose the data of your jobs, which are not MapReduce, right? So you don't want to do that. So these are the motivations why we did the application history server. So let's a little bit talk about what is application history server is and what it can do. So it's a separate daemon. You can run it anywhere. You can run the RM machine, or you can run anywhere else. It's up to you. It has a pluggable storage, so you can plug any kind of storage. So they're very cleanly defined interfaces are there, reader and writer. So you can define your storage based on those interfaces. And so currently, by default, we have HDFS interface, and we have in-memory implementation of these interfaces. So you can, so by default, we store it in HDFS. We have in-memory implementation, which we use for all kind of testing the daemon and testing for the test cases, etc. Right? So this is very handy. You have in-memory implementation. By default, it comes with the HDFS implementation. And resource manager directly writes to as soon as the app finishes, resource manager directly writes to the storage by using writer interface. It also can serve the aggregated logs of the job. So if your job is finished, there is a nice UI where you can go and look into their job, and actually you can go and look into their logs as well for the history server. So you can see your job, even if your job is finished, is not running or whatever, your RM crashes or what's happened, you can go and see your logs as well. We have 3 interfaces for accessing application history server, which is UI. We have a command line interface. We have UI, command line interface, and the REST endpoint. So you can actually call, there is a REST endpoint for the service, so you can call all these, you can get all this data through the REST APIs. So for the storage a little bit, I'll talk about, it stores generic data for the application. It stores application level data, like what is the queue, user, etc. All the application specific data it stores. And then it stores for this application, what are the application attempts, what are the, information about each application attempt, where it ran, in which node is ran, all this kind of information. How many containers what is the master container, all that kind of information of the application attempt it stores. It also stores all the list of containers, about all the information, generic information about the containers itself, like what are the resources it used, where it ran, where is the log location, etc. So all the generic, which is, I mean, there is a generic data and there is a framework-specific data. So all the generic data, which is which is very much specific, I mean, which is generic enough for all the application, it stores, and we don't store anything which is application-specific data, like MapReduce. We don't store like MapReduce job, counters, etc. So for that, we have this timeline server, which Shiji will talk about a little bit, that stores all that. So this is the simple architecture for the history server, which is you have RM, which RM writes the RM apps, attempts, and the containers into the history through the writing service using a writer interface to the storage. And this is a multiple thread, so as soon as the application finishes, it writes. So there are multiple threads, so this is how you're not blocked, this is not serial. So as soon as any application finishes, it writes the data. So there is a user, and then there are web UI, REST APIs you can use to get the data, and you can get the specific data for the applications. And then you have an application, so there is a CLI, so we have an application history protocol where you can directly use CLI to get the data, as well as then you have reader. So how it does is it uses a reader interface. A reader interface goes to the storage, gets the data, and serve to the users. The storage is we have two, which is I just explained, the HDFS and the memory. You can write your own storage if you want. The CLI interface is very simple. You just do a yarn application status, application ID, and you'll get all the data. And this is seamless. I mean, there is no specification of the history here. So if the application is running, it will get the data from the RM because the application is running. And if the application is finished, it will get the data from the history server. So that is seamless. So there is no other interface for the users to get the data. I mean, this is same interface you can get for the running application or for the completed application. So there is no new interface for the users. So this is how you get it. This is a couple of examples how you get the application data, how you get the application attempt data. You can list all the application attempt for this application, and similarly you can do the containers as well. This is a simple REST API where you can use it for getting the data from the REST protocol. So you just specify the server where the application history server is running, and then specify the application ID and get the data. And similarly, you can do it for the application attempt as well as for the containers. A little bit talk about of the scalability for the storage. For the application history server, we have one file per application. So we don't want to, initially we thought of having multiple, one file for application and then application attempts, and for the containers, then we thought it's not going to scale. We did some experiments and then it was not working. So we actually had one file for application, and as soon as we get a finish event for a container or an application, we keep on writing it on the same file, and then we aggregate at the reader interface, at the reader service, based on the data in that file. So we have one file per application. The format of the file is protobuf, so we just directly write the protobufs on the file. So we did some experiments of the file, which is size of the file is, if you have 100 containers, the size of the file is 19 KB. If you have 1K task in your job, it's 184 KB. If you have 10K task in your job, the file size was 1.8 MB. And if you have 100K task in your job, the file was 19 MB, which is pretty much reasonable for storing a lot of data into the HDFS. Multiple RM threads write to the history storage, so in that sense, we probably can scale further in terms of we are not blocking the users, the applications to write into the history stuff. So yeah, timeline server, I think Shiji will talk about it.
Okay, thanks, Mayank. So in the second half, I would like to go over something about the timeline server, which is a pretty new piece of the Yarn since Yarn 2.4 release. So what the timeline server is, in general, it is something that allows your applications to upload some your application-specific information to that place, and then later on, your users can come back to query this information, to use this information to do the analysis about your application, to see how your application was working on a Yarn cluster. So the motivation for us to do that has 2 points. The first of all, we would like to have Yarn to take care of the monitoring service, such that your application is going to get rid of the workload for the monitoring work. And your developers for the Yarn application could focus on your business logic only. The second thing is for the application diversity. Now you can see we have a number of different applications can running on the Yarn platform, such as MapReduce, Storm, Spark, Test. So different applications have completely different logic and workflows. They have some unique information, which is only makes sense to their application. They want to put this information into some place and for the later usage. So for these 2 reasons, we want to make a timeline server to give users the option to upload the application-specific information in addition to the service we already provide to users to get the general application information. So first, let's look into the data model of the timeline server. This is something we would like to provide the user, and the application needs to think about how they want to compose their application information according to this data model to provide it to the timeline server. There are 3 things I would like to highlight here. The first one is entity type. It is actually an abstract concept. It could be anything. For example, we can consider an application is an entity type. We can also think about a part of the task of an application is an entity type. And within the scope of the one application, we don't have any limitation on how many entity type you can define. The next thing is the entity. The entity is actually a concrete instance of an entity type. And here we allow people to, the developers to construct the connections, the relationship between any 2 entities. And within each entity, we allow the user to define the event. The event is used to describe what something happens to this entity. So we believe with these 3 types of things, users can easily define the application-specific things such as metadata and a metrics and pass it to the timeline server. Then let's look at the architecture of the timeline server to see how it works. The architecture is actually simple. At the frontier of the timeline server is a REST service. It's going to take the response from the client, the request from the client. It can be the request to put the timeline data. It also could be the request to fetch the timeline data. The service tier is going to interact with the back end to call the timeline store reader and writer to persist the data into the database or to fetch the data out of the database. To make the whole thing work, there are 3 major parts, and I would like to highlight these 3 things in the following slides. The first one is about store. Our timeline store is now backed by the LevelDB store. The reason why we would like to choose the LevelDB has 3 points. The first of all, the LevelDB as a key value store. It is a perfect match for our data model. The second thing is that the LevelDB is a lightweight database. It is easily to be deployed on a machine and use the local file systems. Don't need any configuration. The third thing is that the license of the LevelDB is also compatible with the Apache license, so we can integrate into our the YARN architecture. So when we have the LevelDB store, we wrap it over with a reader and the writer interface. The reader and the writer interface will take the timeline entity and the event as input, translate into some keys and values, and persist into the store. On the other side, it will get the keys and values from the LevelDB and compose them into the entities and events and get back to the user. One thing I would like to mention here, when we implement our timeline store, we think about the data retention. This is because the YARN cluster is supposed to run for a long time, and many applications will come into the cluster and submit the data to the timeline store. So some data is going to be very old, and the users are not going to use it anymore. But if we do not delete this data, the store is going to keep growing. So at some point in the future, the timeline store will use up all the disk space of the machine. So we would like to get rid of this situation. So we introduce the data retention mechanism here to discard the old data. The next piece is client. This is rationale when we developing YARN. So we are always trying to provide the easiest way for developers to write a YARN application. So what the timeline client does is to wrap over the REST APIs to post the timeline data for the users. So with these tools, what the developers need to do is quite simple. You just need to think about what is going to be the critical information you want to put into the timeline server, and compose your timeline entity and the timeline event, and then use the timeline client to post the data to the timeline server. And the one thing I would like to highlight here is that the timeline client can be used in your client side, can be used in your application master, as well as in your container. That means where you have something that you think is important to be noted down for later usage, you can use the timeline client to send it to the timeline server. The third thing is the REST APIs. So later, when you have some data stored in the timeline server, your users is going back to query this data to do some analysis. So we provide 3 APIs for the users. The first one is getting the timeline entities of a given entity type. The second one is to get a specific timeline entity. The third one is to get the event streams. And we think that via these 3 APIs, we can address most use cases. The next thing I would like to mention here is about security. Since applications are going to send some confidential data to the timeline server, we would like to protect your data to prevent it being extracted by some anonymous users. So we would like to make the timeline server to work in a secure mode as well. To do this, we have borrowed the succeed experience from the security of other Hadoop components. So what we have done here includes the authentication negotiation by the Spanangle over HTTP protocol. And we also support the authentication via the Kerberos plus a delegation token. There are 2 reasons why we choose to use delegation token here. First of it is for the performance consideration. let's say if we have a lot of incoming requests that need to be authenticated by the Kerberos server, then the Kerberos server will become the bottleneck for the scalability of the timeline server. The second consideration is that actually we said we will allow the client to be called from the application master and from the containers. The application master and containers may not be run on a local machine. It may run on any machine in a Yarn cluster. So at that machine, your application master or container may even not have the Kerberos principle. So what we can do here is actually at the client side, to get a delegation token from the timeline server and make use of the current Yarn stack to spread the delegation token to your application master in a container, such that your timeline client can get this delegation token and use this delegation token to talk to the timeline server and pass the authentication layer. The last but not least thing here is access control. Here we are doing something similar to what we have done for resource manager application access control. We make an access manager, and we just allow the administrators and the owner of the timeline data to access this data. And we do the access control at the entity level, which means if a user is granted the access to the entity, it can also get the access to all the events that belong to this entity. That is pretty much for the current timeline server. And the timeline server is still under development, and it's not fully production ready. But one thing we would like to highlight here is that we already have our customer. Here is a use case. The Hive on test has already integrated a timeline server to do the monitoring stuff. What they are doing is that when a Hive job is running, the Hive client is going to send some Hive-related information to the timeline server. And if the Hive is backed by the test engine, the test workflow in the Yarn cluster is also going to send some test information to the timeline server. On the other side, they make use another tool which is called Embry. That is the Hadoop management and monitoring tools to query the Hive on test information from the timeline server and plot it into some nice graphs for users to understand the performance of a Hive job. Here is a snapshot we have obtained from one Embry page. On the left side, you can see there's a nice graph, a number of map blockers and the reduce blocks are connected together. It is an execution workflow of a Hive job. The information that be used to plot this graph is completely come from the timeline server. This is another nice graph. As I have mentioned before, the information are also come from the timeline server. Here you can see each row is actually a container. It is showing the sequence of mapper tasks that is running on that containers. The width of the map task block is actually defined by the map start event and the map stop event that has been stored in the timeline server. That is pretty much from the timeline server side. And as I have introduced before, the timeline server is still under development, and this is in the same situation for the generic history. So we are still working hard to make these two things better and better to make it production ready. In the following, I would like to introduce some features, something that we are going to do in the future. First of all, we would like to do the integration between the generic application history and the timeline data. Currently, these two pieces are completely orthogonal, and though they are living in the same daemon. In the future, what we want to do is to move the generic history data into the timeline store as well, as we have already proved it is possible to let the generic history to make use of timeline and data model. The second thing is rebasing the MapReduce job history server. Given the timeline server is ready, we do not need to spend additional effort to maintain a specific job history server for MapReduce. What MapReduce can do is to, instead of writing the history into some files on HDFS, they can simply post this information, such as the counter information, mapper information, reducer information, to the timeline server directly. The last but not least thing here is rendering the data on timeline server. Actually, I think this would be a nice piece. If you look back to the last case I have just showed, we need to pull the data out of the timeline server and to render the data on a third-party tools, or you can render the data in your application yourself. But there's an overhead to migrate data from one part to the other. What we would like to do in the long-term future is to not only allow your application to upload your data, we also allow you upload the logic to render your data. So after that, your users can just come to the timeline server to see the data according to the logic you want to render it. And there is another thing what we are doing now. It's scalability about the timeline service. It is currently under development, and it's doing by Mac. Maybe Mac want to give more points here.
Thanks, Shiji. So yeah, we looked at the timeline store, and then we found out that it's not gonna. So the level DB is not going to handle the scale which we run at eBay. So we probably need to do something smart here. So yeah, level DB is good for small applications. I mean, from small clusters, it will work well. Actually, we tested it works well. But the scale which I think eBay runs, we need something else. So we need something which we can horizontally scale, where we can put more hardware or and more servers. By that, if the load's increasing, we can actually scale it. So we looked at it. The data model which we chose before was a key value. So the timeline store have the data model key and value. So we looked at, so we need something similar. So we actually choose HBase, where actually all the application directly write to the HBase store, where so it serves both the purposes. It has key value store and it is horizontally scaled. And we don't need any middle tier server which will be distributing the load between the HBase. So we probably will want all the application master will through REST API directly write into the HBase. So we eliminate all the scaling issue in between. So this is what we are actually working on. The Jira is Yarn 20322. Take a look. Patch is already there for HBase. We are in the reviews. So we already, so the Jira numbers for the history server is 320, Yarn 321. For the application timeline is 1530. Yeah. Please, there are a lot of Jiras which are open and unassigned. Please take a look and assign it to yourself. And also I want to take this opportunity to thank you, Billy and Vinod from Hottenworks, who helped us a lot in this work. We will, I mean, if you guys can have any questions, we can take it now.
I
have a quick question. Like, is there any dependency if application history server goes down? Does it impact Yarn in any way?
So there is a, so if the application history server goes down, it will come, I mean, we can restart it. There is no HA as of now. We haven't worked on the HA as of now. But if it goes down, the history, all the historical information is in the store. So as soon as we can restart the history server, it can build its state from the history store.
So does it impact the jobs or anything that's going on the Yarn cluster in any way?
No, we haven't seen that, and I don't think architecturally it's going to happen. The only thing is if the history server is down, probably whatever the application is writing is not able to write into the store. But from the HBase store, it will eliminate that as well because we're directly writing to the store. So even if the history server goes down, the only thing is clients cannot access it.
Right. So does the application history server use HDFS or?
So application history server use HDFS. Application timeline server use level DB. But we are writing to the HBase. Other than that, it has a writer interface and the reader clearly defined. So even if you don't want, you don't like HBase or level DB, you can write your own store. It's pretty simple. It's very simple. Right.
Thanks.
I have another question. Do you support the restart of a crashed app?
Can you see the question?
Say the application crashes, when it restarts, it can reuse whatever they already computes or stores? Or
Yes, actually the same as that. Application crash is also one life cycle of actually one step of the complete life cycle of the application on Yarn. So from Yarn perspective, if your application got crashed, they still have maintained the complete state of the final status of your application. So that means all the information, actually for the application history server, we push all the information after the complete application cycle has been finished on the resource manager side. So you don't need to be worried about the information get lost or other things caused by your application crash.
Okay, thank you.
How about the overhead for these two servers?
Do you mean the problems of we have two servers instead of one?
No, I mean the performance overhead.
Yeah, actually we have done a bunch of performance testing before we push this stuff out. In general, we can say it is good. We can, Mac, would you mind go back to one slide that you have shown some numbers about the files. I remember if let's assume we have a very big applications and keep using open the containers and writing the history data, it will only take maybe tens of megabytes to store the whole history things. And from the timeline side, I cannot remember the exact numbers, but according to our test, we can simultaneously handle hundreds of applications posting data together.
And from application perspective also, I don't think it's an overhead because it's just a REST API. They just keep on writing onto the server.
Any questions?
Okay. Thanks, guys.